Welcome back for another video in the OpenStax Calculus 1 video series, an in-depth view of mathematics. In section 6.2, we're actually talking about two major topics. So I've split the lecture notes and I've split the video into two different sections. In the first part of section 6.2, we want to take a look at solids whose cross sections are all the same shape, but not the same size. For example, what we're talking about with a cross section is taking some solid object, such as the one that I have here, and slicing it parallel to one of the axes. Now, you could slice it along any particular line, but the ones we'll be looking at will be sliced either parallel to X or parallel to Y. This makes our work easier to do. When we slice them parallel to that one and look at the cross sections of each piece, in this shape, they all turn out to be squares. In some shapes, they might all turn out to be right triangles or even semicircles. The sizes are all different because it goes up in height and then comes back down. The size of all the squares are different, but they're all squares if I slice in this direction. We want to be able to compute the volume of a solid, which has cross sections that are all the same shape, but of different sizes. In order to do that, we'll make an approximation. We're going to take a partition, just as we've done before with Riemann sums. And we're going to assume that on each little partition, the square is the same size on both sides. That makes it into a regular solid, and we can find the volume of a regular solid by taking the area of the base, which is the cross section, multiplied by the height, which is the distance between the two squares. Well, that is actually the width of the partition, which will be either dx or dy. So when we're looking at these, we can approximate the volume by finding the volumes of each individual square and adding them together. Then we take the limit as the number of squares goes to infinity, and this will give us the volume of the solid. It sounds like, and it is, a Riemann sum. And of course, it becomes a definite integral. Now, let's think about what the bases are. When you take the shape, the bases are not necessarily what it's sitting on. A base for this shape are the two sides whose cross sections are identical, the two sides that look like squares. And the height is the distance between them, not the vertical height in this case. Now, when we're thinking about these, notice that the cross sections get different as you go from one side to the other. In this particular case, this side is a circle, which means that the length of the bottom of the square is given by the distance across the circle, the diameter. And since we know how to find the diameter of the circle, we can actually compute the volume of each individual square. When we're looking at it, I simply compute the diameter and multiply it by itself to get the area of one of the square shapes. Then I multiply by the differential, the thickness of that slice, to get the volume of that slice. Let's take a look at a pyramid. A pyramid is a good shape where we'll be wanting to find the volume of it. In this case, the bottom of the pyramid is in fact a square, and it comes up to a point called the apex. If I slice parallel to the base, the square, I get a lot of other squares, but they get smaller as I go from the bottom to the top. The cross sections parallel to the square base are all squares, but the sizes are changing. So I approximate by making slices where both sides are squares of the same size, and I find the area of the square and multiply by the differential. which in this case would be dy. That gives me the volume of one slice, and then I add up the other slices. In this video, we're only going to be looking at finding the volume of these kinds of solids. Let me switch now to a different screen so you can see the shapes more clearly, and I'll show you some examples of other solids where the cross sections are the same shape, but not the same size. The one we started with was this one. And as you look at it, you can see that it's divided into a bunch of squares. Each shape is a square, but the bottom, again, is a circle. We find the length of one side of each square by finding the distance between the y values on the circle. It's not going to be the diameter, except at the center. For this one, I need to find the y value at this x-coordinate minus the y value at that coordinate. In other words, I need the equation for the upper half of the circle and the equation for the lower half of the circle. And then I can find the length of this side of the square by subtracting the lower half from the upper half. That will give me the distance between these 2 points. Again, it's only the diameter in the very center of the circle. Let's look at another one. This is another one where the cross sections are all squares. I have to hold it at an angle so it shows up in the light. Maybe a different colors would have been better. You can see they're all squares, but the other side is not, in fact, a circle. It's a parabola. Whether it opens up or opens down, I can find the length of one side of the square by computing the y values between this horizontal line and the parabola. And that will give me the length of one square at each x value as I move from one side to the other. And then, because the cross sections are all squares, I can find the volume of each slice by taking the area of the square times the slice, and then adding them all together. The last one I have, the cross sections are all semicircles. In this case, the shape that would give the values is in fact a right triangle, and I've kind of lost my top. You can see when I break it open that in fact all the cross sections are semicircles. In this case, when I'm trying to find the volume, what I need to know is this distance here. This is, in fact, the diameter of each individual circular slice. And I can find the area by taking half of that diameter and multiplying by pi r squared by 1/2. That will give me the area of the slice, and then I multiply by the differential to get the volume. And I add them all together. Again, I can use the right triangle base to find this distance here. Let's go ahead now and introduce some terminology that will make this simpler to do and will help you to understand what's happening. For many students, this is a very difficult topic, and these are very difficult problems. So we're going to work a couple examples as well. Let's now turn our attention to more of the theory and the terminology. First, let's talk about the cross-section. The cross-section of these solids can be defined as the intersection of the solid with a plane, where a plane, of course, is basically a line cutting through in one dimension. In each of the following shapes we're going to look at, the plane is given by the vertical line x equal to some constant. In other words, you're cutting through there with vertical lines which are parallel to the y-axis. For some solids, the plane that you cut with is horizontal, y equal to a constant, meaning that you're actually cutting parallel to the x-axis. In all of our examples, we'll slice parallel to X or Y. It is, of course, possible to slice on some other plane, but that makes the computation of the volume much more complicated. Let's imagine slicing through these solids with a very large sharp knife like a guillotine. After slicing it open, we want to look at the cutaway shapes. So for example, on this one, when you slice it apart, what do the insides look like? Do those shapes match the base shapes? If they do, then that's the kind of solid we're talking about. In this particular problem that you see here, we have, I believe, a sine function on one side, and I can't remember, part of a parabola or something on the other side. But if you look at this on the side, you can see that the cross sections are in fact all squares. The function on the top and the function on the bottom is a little bit different. This is actually coming from a GeoGebra applet, which you see the link for here. Let's take a look at the applet so we can rotate this picture. In the first picture, it turns out that the function, the upper function, is a downward opening parabola, and the lower function is a version of sine, which explains the wiggle that we have going on. In this case, we're looking between x equal -8 and x equal 8, and we've partitioned it into 9 different slices. When you look up here and we rotate, you can see that the shapes on each side are the same, and the function there on top is the downward opening parabola with the sine function below it. Note this sine function was shifted down. In this particular case, all of the cross sections are equilateral triangles. You can see it's checked up here at the top. That means that the length of all sides of the triangle are the same. How would we find the volume of one of those slices? Well, since all the sides are the same, and because the area of a triangle is 1/2 the base times the height, I need to know how long one side is. To find that, I can again rotate it so that I can see that one side of that slice has an upper value on f of x and a lower value on g of x. So at this x coordinate, f of x minus g of x gives me the length of that side. And since I know it's an equilateral triangle, I know the angles are all 60 degrees, and I can use trigonometry to find the height. That will give me the area of one slice. Now, that's not volume. To get the volume, you have to multiply the area of that common shape by the differential, which is this small distance here between the two. That is the differential, in this case, dx, because I was slicing parallel to y, dividing up the x-axis into smaller subintervals. In this particular applet, you can change the cross sections from equilateral triangles to isosceles right triangles. It will change the volume of the solid. We can also change it to squares. And again, we get a slightly different volume. We'll get a different solid altogether. We can even do pentagons, which are 5-sided shapes, but will not work with any of those since the area of a pentagon is more difficult. You can also do semicircles, but GeoGebra has a hard time showing the semicircular slice. So all it does is show the cross sections. Cross sections are all half circles. And again, the diameter of each individual slice is given by f of x minus g of x. You can take half of that to get the radius, and then find the area of that semicircle with 1/2 pi r squared. Then we multiply by the differential to get the volume. Let's now take a look over here at some other pictures. In this picture, we want to describe and define what we mean by a cylinder. Now, most students, when you say cylinder, they have in their heads something more or less like a soda can. It has a circular base. Better pick up one that's empty. It has a circular base. Yes, I'm addicted to Coke Zero. And it has a height. And it is at a right angle to the bottom. Notice that if you were to slice it parallel to the circular bottom, all the cross sections would be circles. But they wouldn't be different sizes. They'd all be the same size. Now, in mathematics, when we talk about a cylinder, we're actually talking about any three-dimensional object that has two sides that are the same size and same shape, like the right circular cylinder or Coke can. And all the cross sections parallel to the two bases are also exactly the same size and shape. Here are some examples of what is considered a cylinder in mathematics. You'll see this idea coming back in Calculus 3, where we deal more with three-dimensional objects. We think of the cylinder as a tube, but really in math, it can be any two-dimensional shape pulled along a line, creating a three-dimensional solid. In this shape right here, we would call it a triangular prism, but it is in fact a cylinder. This end is an isosceles triangle, and this end is an isosceles triangle of the same size and shape. If I slice parallel to those sides, every cross section is the same size and the same shape. This is what we think of as a cylinder, but they're both cylinders. The base, of course, is one of the ends of the object where all the cross sections are the same size and same shape. The base is not necessarily what it's sitting on. In the picture up here of the prism, the base is the triangular end on each side. It is not the rectangle that it's actually sitting on. Base does not mean I'm on the bottom. In this case, it means I have the same size and shape as the one on the other end, and all our cross sections parallel to us in between are also the same size and shape. Then we refer to what we call the height. The height is given by the distance between the two bases. Here again, the bases have the same size and same shape. Here are some more pictures of cylinders where I've identified the base and the height. Remember that height in this case may not be the vertical distance. Height is simply the distance between the two bases. In the first three pictures, I have the same rectangular box. In the first picture, I'm thinking of the left side and the right side as the bases, and that makes the distance in between them the height. In the middle picture, I'm thinking of the top side and bottom side as the bases, and that makes the height actually the height of the box as we would normally think of it. This time I'm slicing parallel to the bottom or horizontally. In the first picture, I would be slicing in this direction straight across. In this third one, I'm trying to figure out what I'm doing here. I'm looking at the back side of the box, and the front side of the box is the bases. That makes the height in between them the distance. Now let's look at this picture right here. It is half of a right circular cylinder. This edge looks like a semicircle, and so does the one in the back. If we slice parallel to the semicircles, all the cross sections are semicircles, same size, same shape. That makes the distance between the two bases the height. When we look at a Toblerone candy box, we can see the same thing happening. The equilateral triangle on either end is the base, and the height is the distance between them, even though it's sitting on a rectangular bottom. When we look at this, notice again that we're slicing parallel to the bases along the height. When we look at it in this orientation, a right circular cylinder, the circular bottom and top are the bases, and the height is the vertical distance as we're used to thinking of it. We would slice parallel to the bases along the height. This last picture here is a pentagon prism, which is also a cylinder. The left side and the right side are both pentagons, same size, same shape, and all the cross sections as well. The height is the distance between the pentagons, not the vertical distance from the bottom to the top. Now, once you understand what a cylinder is, we can define the volume of it. The volume of any cylinder is the area of one of the bases multiplied by the height. In other words, if we want to look at these pictures, to find the volume of the Toblerone box, I need to find the area of the equilateral triangle and multiply by the distance between the two triangular ends. That will give me the volume of this box. If I'm looking at the pentagon shape, I find the area of one of the pentagons and multiply by the distance between the two pentagon shapes. That's the volume. In other words, the volume is the same formula no matter what shape the base takes on. Area of the base times the height. Let's now look at a slight variation on this. It is possible not to have a right cylinder where the base is at a right angle to the height. You could instead have what's called an oblique cylinder, where it's slanted, where the base is not perpendicular to the slanted edge. However, the volume is still given by the area of the base times the height, but this time the height is measured perpendicular to the bases. We'll not be dealing with any oblique prisms, so you don't have to worry about these. Instead, we'll be dealing largely with pyramid shapes. Pyramid shapes have one shape at the bottom and come up to a single point. They are related, however, to the volume of a cylinder with the same size base that's on the bottom of the pyramid. Let's take a look at pyramid shapes. Like cylinders, pyramids have cross sections that are all the same shape, but they're not the same size. As we saw in the introduction, if you take a square-based pyramid, you slice parallel to the square, you still get squares as you move up, but they get smaller in area. The one next to it is based on, well, it's hard to tell, but it looks kind of like maybe a right triangle. And again, if you slice parallel to it, you'll still get right triangles, but they will be smaller as it gets closer to the point. This one has a 1, 2, 3, 4, 5, 6 hexagonal bottom. And this one is also a triangle, but I think it's isosceles as opposed to a right triangle. And of course, the pyramids in Egypt as well have a pyramidal shape. So we can use the formula we're about to develop to find the volume of a pyramid at Giza. When we're looking at these, it's related to the volume of the cylinder with the same size base as on the largest part of the pyramid. When we're looking at a pyramid, it truly does have a base and a point at the top. If you took that base and created a cylinder instead, where you had the same size base on the other end, you can find that the volume of the pyramid is 1/3 of the volume of that cylinder. In other words, if you want to find the volume of the pyramid, find the volume of the cylinder with the same size base and multiply by 1/3. This means that we can write the formula for the pyramid as 1/3 area of the base times the height. Now let's take a look at some solids that are not exactly cylinders and not exactly pyramids and see how we can combine these ideas. Cross sections are all the same shape, but the sizes vary. In this one, I have the graph of x² - 4, which is here on the bottom, and the graph of -x² + 4 here on the top. What we want to do is we want to look at different cross sections for this particular shape. In this first one, I have equilateral triangle cross sections. If it's an equilateral triangle, again, I can find the length of one side by subtracting the y value on F and the y value on G. That will give me the length of one side, and since I know it's equilateral, I can use trigonometry to find the height. That will give me the area of that triangle. To find the volume of that slice, I multiply by the differential. Let's take a look at some different images of that picture. Here you can see, again, the graph of f of x on the top and the graph of g of x on the bottom. In this case, I've set them all to be isosceles right triangles. When I look at an isosceles right triangle, in this case, isosceles means two of the sides are the same length. And it's a right triangle, so I have a right angle in the corner. In this case, I know that the length, which is the distance between f of x and g of x, has to be the same as the length on this side. And I can find the area since the height and the base are the same. And once I know that, I can find the area to multiply by the differential to get the volume. If we used a different shape instead, like squares or something like that, and I don't know why they all went on the bottom. I need to rotate it. Let's see if I can keep rotating. Well, it won't rotate. We'll just assume they're on the top. Okay. For some reason, it's sticking them all on the bottom and it won't let me fully rotate it. Rats. Okay, well, we'll look at it from the side. There are my pentagon shapes and there are my squares. For a square, the distance of one side would be f of x minus g of x at that x coordinate. And then I could square that value to get the area of the square and multiply by the differential dx. I would have to do that for each slice, which is at a different x coordinate, so the change in the y values will be different. Let's now take a look at some more of the images that we have. We've seen the squares and the triangles and the pentagons. Again, we can compute the volume of one slice. Now, what formula am I actually using when I compute the volume of a slice? That's right, I'm assuming that each slice has the same size and same shape on both sides, and that all the cross sections between in one slice are same size, same shape. That is, each slice can be considered a cylinder, so that the volume of the slice is the area of the base times the differential, in this case dx. We won't have a specific formula for any of the shapes we've just been looking at, but we can come up with a common method in order to find the volume of these solids. Again, we're going to slice parallel to the cross sections that all have the same shape. We're going to create multiple very thin pieces so that we can approximate that each piece is a cylinder, where the two edges are the same size as well as the same shape. And we multiply the area of that cross-section by the differential to get the volume, add them all together, and take the limit as the number of slices goes to infinity. Let's now take a look at the formula. The volume equal to the integral of the leftmost slice's x-coordinate to the upper limit of integration, which is the rightmost slice's x-coordinate. Then we're going to find the integral from a to b of the cross-section area, a of x, with respect to the differential dx. A of x times dx for each slice is the volume of one slice. And by integrating from a to b, we have allowed the number of slices to go to infinity and added them all together. We can also integrate with respect to y by going from the bottommost slice's y-coordinate to the topmost slice's y-coordinate. Then we have to think of the area of the cross-section in terms of y and integrate with respect to y. Let's go ahead and take a look at an example now. In this example, we have a region in quadrant 1 bounded by the coordinate axes, the x-axis and the y-axis, and the curve 1 minus x squared. You can see in the background here the shape. 1 minus x squared is a downward opening parabola, and we only see half of it since we're only interested in quadrant 1. Then we're going to slice this region along the x-axis between 0 and 1 into multiple slices. Each slice will have a width of dx. Now we need to think about what the cross-section shapes are. You'll have to be told what they are since you can't make an assumption. In this case, the solid has the bottom region, which consists of this half of the parabola, and the cross sections, which are parallel to the y-axis, are all squares. You can see in the second picture, it's rotated so that you can see that all the squares are in fact the cross sections. And the volume of each slice becomes the volume of each, well, sliced box, in other words. Because they're squares, we want to find the length of one side. Looking at this, again, we can see that we can take the y value on the parabola and subtract, well, the y value on the x-axis, which is 0. In other words, the y value on the parabola is the length of one side of the square, but it's going to be at different x values. Since we have figured out that the length of the side is 1 minus x squared, and we know the width of the slice is dx, then we can say that the volume of one little slice is going to be the area of the square times the dx. In this case, the area of a square is the side length squared, but our side length is 1 minus x squared, so we square that and multiply by the differential dx. Let's go ahead and complete writing what the definite integral would be. In this problem, we need to be integrating from x equals 0 to x equal 1. We want to take the area as an equation of x and multiply by the height of each little, well, rectangular box, which in fact is the differential dx. This is going to give me the integral from 0 to 1 of 1 minus x squared quantity squared, the area of each little square, times the differential dx. Now that we have it set up, the rest of it is straightforward integration. Go ahead and pause the video to work it out, then turn it back on to check your answer. So let's see how we did. The first thing that I would do would be to go ahead and multiply out the binomial square. This gives you x to the fourth minus 2x squared plus 1 as the new integrand. Then you can simply apply the power rule. When you apply the power rule, you get x to the fifth divided by 5 minus 2x cubed divided by 3 plus x to evaluate between 0 and 1. Because each term has the variable x in it, when I substitute 0, they're all going to turn to 0. In that case, you really don't need to write that part. You could just instead substitute the upper limit of integration. To be safe, I went ahead and wrote it out long ways, but when I'm working for myself, I wouldn't write the 0 part because I know it's going to go to 0. This gives me 1/5 minus 2/3 plus 1, which comes out to be 8/15 cubic units. In other words, a cube, 1 unit on each side, and this is 8/15, which is about half of that. That's the volume of that solid. Let's take a look at that solid in more detail. Here is that solid in this picture right here. You can see the shape right there of the downward opening parabola above the x-axis and to the right of the y-axis. And of course, we've got all of these shapes coming up that are squares. I have 6 boxes here, but you could increase the number of boxes dramatically to get a better idea of what the actual solid looks like. It's very similar to one of the ones I showed you earlier. Let's now take a look at example 2. In example 2, our region is again going to be in quadrant 1, but this time bounded by 2 curves, y equal x cubed and y equal x squared. We want to suppose that we have a solid, and the bottom of the solid is region R. That's not necessarily the base. And the cross sections are perpendicular to the xy plane, and they're parallel to the y-axis. That means that when I slice, I'm slicing up the x-axis because it's parallel to the y. That will make the differential dx again. Each of these slices is a semicircle, but they change in size from one side to the other. You can see in this second picture all of the cross sections, which are semicircles. When you find that shape, it's going to be a cylinder with 2 half circles on each side and the distance between them being the differential. If you look at one of them, you can see that the radius is half the distance between the y value on the upper curve, which is x squared, and the y value on the lower curve, which is x cubed. In order to set up this problem, we again need to find out where they intersect. X squared and x cubed go through the origin and the point 1, 1. So we are integrating between x equals 0 and x equal 1. We need to find the area of one of these semicircles and multiply it by the differential dx. To find the area of the semicircle, I take half of pi r squared. But to find r, I need to take the distance from x squared to x cubed by subtracting x cubed from x squared. That would give me the diameter of the distance, the diameter of the semicircle. But I want radius, so I take half of that. Then I square it to get the area. It is a semicircle, so I have 1/2 pi r squared. When I multiply this out and I square the 1/2, I get 1/4 times the other 1/2 gives me 1/8. If you multiply out x squared minus x cubed, quantity squared, you will get x to the 6th minus 2x to the 5th plus x to the 4th. This is a formula for the area of each cross section, each little slice's base. That was hard to say. Now let's multiply by the differential dx and integrate from 0 to 1. In order to find the volume of this crescent-shaped solid with semicircle cross sections, we need to integrate the area function from 0 to 1 with respect to x. Let's take a look at the work and see what it looks like. In this case, we can apply the integral rule, power rule for integrals, and then we can substitute the limits of integration. Because the lower limit of integration is 0, every term has x in it. I know those will zero out, so I don't need to write them. Substituting in the upper limit of integration would be x equal 1, but 1 to any power is 1, which gives me 1/7 minus 2/6 plus 1/5, all combined and multiplied by pi over 8, which I kept outside as a constant factor. The lowest common denominator or multiple is in fact the product of 3, 7, and 5. And this gives us 105. Getting common denominators and combining the fraction gives us pi divided by 840 cubic units. This is a tiny, tiny amount of volume. This is the end of the first video on section 6.2, where we took a look at finding the volume of solids with same shape cross sections. In the next video, we're going to take a function and revolve it around the x or y axis and find the volume of the resulting shape. Join me for the next video where we explore volumes of revolution.